My name is Stephanie Getty. I use micro and nanotechnology to make better scientific instruments for spaceflight.
My name is John Hagopian. I'm an optical physicist at the NASA Goddard Space Flight Center. The exciting part about this work is it's kind of pushing new boundaries on what we do with nanotechnology in terms of optics.
It is a hollow tube that's made entirely out of carbon, and the diameter is a nanometer. If this were the size of an actual nanotube and you were to scale me up proportionately, then I would be tall enough to reach the moon. Because the nanotubes are so small, we can only use a scanning electron microscope to be able to see them. The method that we use is called catalyst-assisted chemical vapor deposition, and that grows carbon nanotubes on a substrate.
Put the substrate in this tube. You heat the tube up to about 750 degrees centigrade and you flow a gas, and the gas has carbon in it. Because of the catalyst layer, you start to assemble these tubes. Carbon takes a very specific form as it grows.
So one example where carbon nanotubes can enhance the performance of a scientific instrument in space is through their ability to absorb light.
The Z306 paint is the blackest thing that we put on instruments right now. The fact that we're blacker than that, I guess, makes us blacker than black in terms of performance. When light from the Earth or a star hits an instrument or structures inside of the instrument, it gets scattered over all angles. A lot of the data gets contaminated. So it turns out up to 40% of the data could be unusable.
So the current telescopes use black paint to reduce the reflection, but the black paint isn't perfect. It still shows a reflection.
Over the course of our work, we were able to optimize the carbon nanotubes to make them 10 times darker than the paint.
You could get a better observational efficiency. You're not throwing away 40% of your data. The Goddard samples were grown multi-walled, so they're not just single-walled nanotubes, and they're also oriented straight up and down. The reason that the oriented samples are darker is because they're low density, light can go in, it gets rattled around in there and it gets absorbed.
4, 3, 2, 1, and liftoff.
So when we prepare a new technology for space flight, we need to consider the different environments that that technology is going to experience.
If we're going to fly something in space, we can't have the nanotubes falling off and contaminating mirrors, so we had to make sure that they were very robust. Over a long period of time after all these experiments, we discovered that alumina is really the trick to getting the nanotubes to stick. So now you have to scratch them off. They're very robust.
So we are interested in vibration testing for these carbon nanotubes to determine how well they adhere to the substrate and whether they will be liberated during launch. The other thing that we do test is thermal conditions. When your spacecraft is flying through space, it gets very cold, and actually it gets exposed to radiation. And so those are two of the other tests that we expose our technologies to before we fly them.
And the first instrument that we're using them on right now is actually ORCA. That's an earth science instrument. Another thing that we've looked at is using them on LISA, which is a gravity wave experiment.
One area where carbon nanotubes have made it into the marketplace is in sporting goods to make stronger, more robust, lighter weight bicycle frames, tennis rackets. Those are some examples of where you can go out and buy carbon nanotube composites.
At this point, we feel like we have nanotubes that are robust. We can grow them on different materials. They're very dark. So we're very close now to getting to the point where we're going to qualify these for spaceflight use.